Hello. So today I want to speak about the nature of quantum measurement. Um, Quantum measurement? Well, to be more precise, the measurement itself is classical. Okay. So when we measure something, we usually employ some sort of machine which we have built, and typically it is a machine that we can see with our own eyes. So in a pretty usual sense of the word, the machine that's being used to measure something is a classical object, whereas the object that we're trying to measure is in a quantum state. Okay, so when we say when we use a phrase like quantum measurements, what we really mean is that there is this apparently some sort of quantum world or quantum state, and then we're using some sort of a classical. Uh, I should use the word probe. We're using some sort of classical probe to decide just exactly what this quantum state is. Okay, so in the classical system, or in the case of a classical computer, that's a pretty straightforward process. Okay, so let's say I have some sort of bit that's in a state zero, and the way I can be certain that this bit in a computing processor is in a state of zero is by, for example, like measuring the voltage on this particular piece of bit. And if in the case that I measure a voltage equal to zero, then I'm certain that this bit was in this state of zero. Whereas if I measure the voltage and the voltage turns out to be, let's say, 1 volt for this bit, then this physical system was for sure in a state of 1. Okay, so in the classical measurements, as would completely agree with our everyday expectation, what we measure is is what was there to begin with. So let me phrase that one more time in a slightly different way. So if I measure a zero, that's only because the thing that we were trying to measure was really in a state of zero. If I measured a number that was 1, that's only because the state that we were trying to measure was really in a state of 1. Okay? I mean, this is not only true, but sounds almost trivial, right? Because, I mean, the entire reason why we measure something and read off some number like zeros and ones is because the thing was in that state of zeros and ones. Okay, so the reason why I keep saying this dumb thing over and over again is that this kind of one-to-one correspondence uh, between what we measure and what there really was, between what we measure and what the state really was, basically fails. There's no one-to-one correspondence. Okay? So let me give you a simple illustration. Let's say I have this quantum system, and since we're going to talk about quantum computers a lot, and let me be more specific and say that this quantum system consists of several different qubits. Okay, so this is a qubit number one. This is a qubit number two, three, four. Okay, so let's say there's only four qubits in this quantum system, and I hit this quantum system with some measurement apparatus, only to find that this measurement gave me a series of binary numbers like 0010. Okay, so maybe here's another thing that I need to emphasize before it's too late. Although the the thing that we are manipulate, the thing that we're trying to manipulate, and the thing we're trying to do a measurement on is a quantum system, but the actual outcome of the measurement itself is very classical. Actual outcome of measurement is classical. So in this regard, the measurements on a quantum computer is really not that different from the measurements on a classical computer, where the measurements is in terms of numbers like zeros and ones. Well, actually, even for a quantum computer, the measurements on a quantum computer is a string of numbers like zeros and ones. Okay, so at this point, it doesn't seem to be any different between a quantum computer and a classical computer. But the key difference now arises in the fact that the this measurement does not mean that the original quantum state was in a state of 00 and 10. Okay, this simply does not hold. Okay, so for a classical computer, this is complete nonsense, right? If you measured a 0010 on a classical computer, you can be certain with 100% confidence that the classical computer itself was in a state of 0010. Now, you come up with the same outcome on a quantum computer and you find 0010, but it does not tell you with any certainty whatsoever that that the original quantum state was also in the state of 00 and 10. Okay, so this is what I mean by the statement that this sort of one-to-one correspondence between the measurement and the actual state of the physical system, that kind of one-to-one correspondence fails when you make a measurement in a quantum state. Instead, here's what will happen. Now, someone else comes along and so let's say this was a measurement done by person A, and then person B comes along. He takes the same quantum state and does his own measurements on these quantum state. And strangely enough, instead of finding 00 and 10, he finds, or he measures 0, 1, 0, 1. Okay. So then if this was the outcome of classical measurements on a classical computer, we would immediately conclude that at least one of these two people must have made a mistake. Or maybe they were not looking at the same state to begin with. That's why they were giving out different outcomes. But in the quantum world, that this sort of thing can very well happen without any paradox or any conflict of logic. In fact, you can say this is the essence of quantum world. I should just say essence of quantum. And so I'm gonna go into the formulation more deeply as we move along, but in the formulation of quantum mechanics, there is a way to express these different outcomes of a measurement. And the way to express that is by saying that a given quantum state is in a superposition of these two different possible states. Okay, so this is one possible state, and this is another possible state. And each state is multiplied by some number. And then you just add these two states together. And that's the true description of the quantum state. Okay, and the fundamental rule of quantum mechanics is that if you do a measurement on such a superposition of a quantum state, then the probability of your measurements finding the 0010 sequence of bits is given by the square of the amplitude of these number alpha. And the probability that your measurement will yield the other string of bits 0100, 0101 is given by the square amplitude of these second complex coefficient. Okay, so then the nature of the quantum measurements is something like this. Suppose that this alpha square turned out to be 0.3 and this beta square turned out to be 0.7. Okay. Now, you keep making measurements on these quantum state. And for the sake of argument, let's say you made the 10 measurements. Then out of these 10 measurements, about 7 times you will find that the outcome of the measurement is 0010. And about 3 out of 10 times you will find the outcome to be 0101. Okay. So in fact, the different outcomes for different measurements is not at all inconsistent with the rules of quantum mechanics. In fact, the rules of quantum mechanics is inherently probabilistic. So the best that the quantum mechanics can tell you is the probability of your measurements giving out some set of numbers. It does not tell you with certainty that a particular string of 0 and 1s will be the result of your measurement. Okay? Now, you might want to sit on this statement for a while because this is really very different from the way that we normally perceive the idea of measurement. Okay? For instance, let's say you just bought a chair, um, and then you try to measure the weight of that chair, and you put that chair on a scale, and then you read off the numbers on the scale. And the first time you try that, let's say you read off a 10 kilogram for the weight of that chair. And then 5 seconds later, you do the same measurement and you find that the weight actually turned out to be 10.1 kilogram instead of 10.0 kilogram. But that sort of inconsistency is not surprising in almost everyday life. And what you do is simply make several different measurements and then try to sharpen your estimate of the mass by simply taking the average over the values you got from several different measurements. Okay, that's pretty much what we do in a typical measurement process. Okay, that's not what I'm saying when I say that the outcome of a quantum measurement depends on each specific measurement event. Okay, so the fundamental difference between the inconsistencies in the reading of the weight of a chair is probably due to the imperfection in the way that the scale had been built, or maybe imperfection in the way that you have placed that chair on the scale. Perhaps if you place the chair on a slightly different position on the surface of the scale, then the reading might change by a tiny bit. Okay. So the inconsistencies in the reading of a classical measurement is due to errors. Okay, or maybe we were just not being careful enough with the way we were measuring things. In the quantum measurements, you can make the measurement process as precise as possible. But even the most precise measurements will have to be probabilistic. Right? So you repeat this sort of measurements over and over and perfect your measurement skills, spending perhaps several years training yourself, maybe spending millions of dollars perfecting your equipment and so on. But no matter how hard you try to improve the measurement process, the fact that the measurement outcome will vary from measurement to measurement, that probabilistic nature of the measurement will never go away. Okay, so maybe I should say it's inherently probabilistic. And there's no way you can completely remove this uncertainty in just what kind of outcome you would expect in a given measurement. Okay, but then that raises a serious confusion, right? Because now you have to start wondering what good is a quantum computer, right? Because the reason, maybe the entire reason why a computer is so useful to us is because, for example, if we run the same algorithm or same calculation on the computer and over again, we know for sure that the outcome will always be the same. I mean, the simplest example would be to type 2 plus 3 into your calculator. It doesn't matter how many thousands or millions of times you do that operation, the answer will always be 4, right? 2 plus 2 is 4. It's never 5 or 3. Okay. But if you try to do something like that on a quantum computer, you might be surprised to find that sometimes the quantum computer would say that 2 plus 2 is 3, and sometimes it would say 2 plus 2 is 4. And the best that the quantum computer can manage is that it shows a much higher probability of finding the outcome of 2 plus 2 operation to be 4 rather than 3 or 5. Okay, even for a simple question such as what is 2 plus 2, the outcome given out by a quantum computer will not be completely deterministic, but rather it will be inherently probabilistic. Well, then why do we even bother to understand and even try, spending millions of dollars to build a quantum computer when the best answers you can ever hope to get from a quantum computer is going to come with some probability? Well, I'm afraid that's the question we will have to address over the next few months, because there's no way I can give you a satisfactory answer to that right now. And even after spending 3 months thinking about this problem, we realized that the answer really doesn't improve very much. It's just in the nature of a quantum computer to give out answers with only a certain probability, but never with a certainty. But then, if that's all we can hope for in a quantum computer, then what good is it? Well, the short answer is that still there are some problems where even that probabilistic answer is much better than the answers you would be able to find from asking the same question on a classical computer. And the reason why that is the case is because if you ask a classical computer to do the same calculation, it would take possibly millions or even billions of years until the classical computer finds you the correct